Okay. In the last lecture, we started with the free body problem, and then we constructed the equation of motion for the ITS body. So, starting with that again, today we derive the equation of motion in the inertial reference frame and the relative motion, and then the barocentric formula. Okay, and thereafter, once these things are over, then we will go into the, because there is no generalized solution. So, we go into the three body restricted problem or restricted three body problem. Okay. So, last time we had this inertial reference frame x, y and z was the origin, r I and r j were the position vectors of two masses, two heavy masses m 1 and m 2. R I j vector was defined, which is r j minus r I. Okay. Then the equation of motion of the ITS particle. So, here we write this as m I and m 2, instead of writing m 2 we write it as m j. Okay. So, of the ITS particle, the mass m I can be written as m I times r I double dot, this is equal to summation j is equal to 1 to n, where j not equal to I, and then m I times m j multiplied by g by r I j whole cube, then multiplied by r I j vector. Okay. Now, this force on the ITS particle, let us say, directed along the I j. Okay. Therefore, the positive sign has been taken here. So, this is our equation number 1. So, this will give us, this gives us 3. So, for the ITS particle, this gives us, we write here for the ITS particle, we get from equation 1 3 scalar second order ordinary differential equation. Okay. So, if we write the equation of motion for all the n particles, then all together we will get 3 n scalar or ordinary differential equation. Therefore, for n particles we get 3 n scalar ordinary differential equations. Okay. Now, the question, obviously, we cannot solve for more than 2 particle system completely. Therefore, even that for the relative motion only, and therefore, for the 3 body system we restrict ourselves to the 3 body system. So, hereafter for our further treatment for the inertial, relative and barycentric formula, we restrict ourselves to the 3 body problem, and therefore, thereafter for finding out the integrals of motion for the n body problem, we treat it in a general way as we have earlier done, using the cross product and the dot product, finding the angular momenta of the system, and then finding the total energy of the system. Okay, so, this way we will try to analyze the 3 body problem, and thereafter we look into the restricted 3 body problem, where we impose certain condition on the 3 body and then try to look into the solution, what kind of solution it leads to. Okay. So, for the 3 body problem, so we have 3 particles here of mass m 1, m 2 and m 3. We assume the mass m 3 to be satellite, say, or and m 1 in this case, suppose this is the earth, and m 2 this indicates the sun. So, for this kind of system, we can develop the equation of motion. So, m 2 let us suppose this is sun, and m 1 this is earth, and m 3 this is satellite. So, we are interested in finding the equation of motion of the mass m 3 with respect to the mass m 1. Now, we can write r 1 3 this is equal to r 3 minus r 1. So, this implies r 1 3 double dot the acceleration, then this will be r 3 double dot minus r 1 double dot. Okay. So, this is our equation number 1. Now, we can find out the acceleration of mass m 1. So, m 1 times r 1 double dot, this will be equal to m 1 times m 2 multiplied by g by r 1 2 whole cube r 1 2, okay. And the force, this force will be directed. So, we are considering the acceleration of this mass. So, force is directed towards this vector r 1 2 vector. Therefore, this positive signs comes in, and the another one, the force acting on mass m 1, this is due to m 3. Okay. So, that will be given by g m 1 m 3 r 1 3 whole cube r 1 3. So, this is our equation number 2. Similarly, we can write the acceleration or the equation of motion of the mass m 3. So, m 3 times r 3 double dot, this will be equal to So, we are now writing the equation of motion of M3. Therefore, the force acting on this is directed opposite to r13 vector and also opposite to the r23 vector due to the mass m1 and m2. Therefore, both of the terms the forces corresponding to these two masses will have negative sign. So, we will have here m1 times m3 divided by r13 whole cube times r13 with a negative sign, and similarly we will have m2 times m3 divided by r23 whole cube times r23. So, this is our equation number 3. Now, dividing the equation 2 by m1 and equation 3 by m3, and then subtracting from the resulting equation 3 the resultant equation 3 the resultant equation 1. Okay. So, and substituting. So, basically dividing equation 2 by m1 and equation 3 by m3 and then subtracting from the resulting equation 3 the resulting equation 1. Okay. Or either we can say that substituting in equation 1 and substituting in equation 1. Okay. So, what we get r13 double dot, this will be equal to minus m1, here g is missing. So, we insert here g. So, g times m1 by r13 whole cube g m2 r23 whole cube, and then from the equation 2 we get minus g m2 times here r12 whole cube r12 minus g m3 r13 whole cube. So, here can we fit here minus g, no, it will not come here. Okay. So, the resulting equation looks like this. We have r13 double dot. So, all the 4 terms are having negative sign. So, this is r13 here. Okay. Now, this is our equation number 4. So, this implies r13 double dot. This we can combine some of the terms together. So, we have this term and this term, they are related to r13, this r13 vector. So, they are related to r13 vector. So, we can combine them together. So, if we combine them, we get here g times m1 plus m2 divided by r13 whole cube r13, and then we get minus gm2 r23 whole cube m2 r12 whole cube r12. Now, using the fact R23 is equal to minus R32. So, we can write here the above equation reduces to R13 double dot, this will be equal to minus G M1 plus M2 R13, and then this will become plus G we can take outside, M2 we can take outside. Inside the bracket we will have R32 divided by R32 whole cube minus R12 divided by R12 whole cube. Okay. So, this is our equation number 5. So, now in this equation number 5, the first term what we see here, this is the direct effect of the, see here the terms are coming due to the M1 and the M2. Okay. So, both the masses M1 and M2 are involved here. So, the first term the direct effect this M1 plus, this is M1 plus M3, not M1 plus M2. We do the correction here, this is M1 plus M3 and M2 has gone outside. So, this is M3. So, this is the direct effect of the, this mass gets neglected, almost this is negligible if we consider the Earth, Sun and the satellite system. So, M3 this is negligible. So, leaving out only the M1 term and M1 term here. So, the first term is the direct effect of the Earth on the satellite. So, this is basically reflecting the direct or the direct gravitational effect of the Earth on the satellite. Just like in the two body system, if we remove this term, so we can see that in the two body system we got the same kind of equation, where M3 was the mass of the body which was orbiting the heavier body. Now, the second term, which consists of Gm2 times R32 by R32 whole cube minus R12 second term. So, this term here and this term here, okay, we analyze them. So, if we look into this term, this is the R32. So, this is the term which is related to the, this is the first term in bracket and this is the second term in bracket. So, this term is the perturbative effect of the sun on the motion of the satellite that is on mass M3. So, this directly tells that if we have only two body M1 and M3 present and M3 is moving around M1. So, if we bring in the third body, which is the second body, which is the m2 here in this case. So, which is the nothing but sun in this case. So, if we bring in the sun, then the sun acts as a perturbation on the motion of the third body around the first body. So, here the satellite is moving around the primary body, which is the earth in this case, and the sun is trying to perturb the orbit of the satellite around the primary body. Okay. So, this is the significance of this term, while the second term we can see from here, this is the term which is related to 1 and 2. So, this is connected to the earth and the sun. So, in this case what happens, that the sun affects the motion of the earth. Okay. So, this is affecting the motion of earth, and in turn, because earth is affecting the motion of the satellite, therefore, ultimately the motion of the satellite gets affected. Okay. So, if the suppose the distance between the sun and the earth, or the m1 and m2 is increased. Okay. So, because of this effect, so ultimately what will happen, the distance between the satellite and the earth will also change. Okay. So, therefore, the effect of the force of the mass m2 on the mass m1, it also affects the motion of the satellite, where which is in this case mass m3. So, if it affects the mass m3, so therefore, this is called the indirect effect of sun. Indirect effect of sun, effect of sun on the satellite, which is here the mass m3. Okay. So, thus we see that the equation of motion of the mass m3, it consists of altogether two terms. The first term, which is the direct effect of the primary body on the satellite, and the second term, which consists of the perturbation term due to the sun. One is directly, another one is indirectly. So, in both way this is arising due to the sun, and therefore, this is called the second term is called the indirect term, and the first is the direct effect of the sun on the satellite, and this acts basically as a perturbative term on the motion of the satellite around the primary body, which is related to this equation. Now, we can describe the motion in a more general way. Suppose we have n number of particles, n number of heavy particles basically, or heavenly body, of which ml, where the subscript L is indicating the satellite. So, the subscript L stands for the satellite. Okay. So, suppose we have n number of particles, of which ml is the satellite. Okay. So, the subscript L will be standing for the satellite. Then we can write the equation 5 in a more general way. So, here let us write this as r1 L, this is the motion of the satellite. Okay. So, motion of the satellite around the first body, that is motion of the satellite around the first body. Okay. So, r1 L double dot, this will be equal to minus g times m1 plus ml divided by r1 L whole cube r1 L. So, here 3 we have replaced by L, okay. And then we will have terms where the instead of only sun being present, there are number of other massive particles present. So, all of them will be acting as a perturbation on the motion of the satellite around the primary body, which is the mass m1. So, we can write here g times summation j is equal to, so first body we have already taken. So, we here we write j is equal to 2 to n and j is not equal to 1. Okay. So, that is very obvious because 1 we have already taken. So, j, and here we are starting from j is equal to 2. So, j is equal to, so we write j is not equal to L in this case. Okay. So, we can write here following the formulation here. So, we can follow the same notation and here we can write R 3, if, instead of 3 we put here L. So, R L and 2 then becomes, it varies from j is equal to 2 to n. So, here we put R L j divided by R L j whole cube minus R 1 j divided by R 1 j whole cube. Okay. So, in a more general way we can write the, even if we do not want to continue with the notation for the primary body as 1, rather we want to write in terms of I. So, we can write it as R I L double dot, this is equal to minus g m I plus m L divided by R I L whole cube plus g j is equal to 2 to n and j is not equal to L and also j is not equal to I. Okay. And R L j by R L j whole cube minus R I j divided by R I j whole cube. This is for the ITH particle. So, equation of motion. So, this indicates the equation of motion of the satellite around the ITH particle slash body. Okay. Once we have got this, so now we go into the barycentric formula. Okay. We try to look into the motion of the particle in the barycenter. Barycenter is nothing but the center of mass of the all the particles. So, let us see what the result we get from that. So, this is our 13.8. Okay, let us consider that these are the number of particles available here, and somewhere this is Mn. Okay. This is Rij. This is Ri. This is Rj. And then we consider that the barycenter of all the particles, it is located somewhere here. So, this is the barycenter which is indicated by B, and we fix a frame at the barycenter, which is parallel to this frame x y z. So, we fix a frame here. So, this is x b, y b and z b, and we know the barycenter property that, and we will also prove later on for the in body system that the barycenter velocity, it remains constant, that is, it does not accelerate. Okay. So, if it does not accelerate, so we can fix a reference frame about this point and use it for the analysis of the motion. Okay. So, now we connect from this mass to this mass, okay, and this we write as r b I. This is the vector directed from barycenter to mass I, and this is a vector directed from barycenter to mass j. So, r b j. So, from here we can see that r b j minus r b I, this is nothing but r j minus r I. Okay. And other way also, let us see we draw a line from here to here, and this is, let us say, this is r b vector, the position of the barycenter with respect to the reference frame x y z. Okay. So, other way also we can write that this r b j we can express as r b j, this will be nothing but r j minus r b, and similarly we can write r b I, this is nothing but r I minus r b, and therefore, this implies r b j minus r b I, this will be equal to r j minus r b minus r I minus r b. Okay. So, this results in r j minus r I. So, r b j minus r b I. Okay. So, the same result we get as we have directly written here. Okay. So, this is our equation number 1. So, we can write this as let us say r b j I. r b j I is a vector. So, the r b j I vector, it will be directed from here to here. So, this is also the vector r b j I, which is directed from the ith mass to the jth mass. So, this can be written as RBJI, this is equal to RBJ minus RBI is equal to RJ minus RI is equal to RJ. Also this we write as RIJ, directed from I to j. So, therefore, we put here I to j, not Bj. Okay. So, therefore, Rj minus Ri is equal to Rij. Okay. Acceleration ITH body now the acceleration of the ITH body can be described using barycentric terms notation. Okay. So, similarly following the same type of notation, we can write RBI minus RBJ, this will be equal to RBJI, and this will nothing be equal to Ri minus Rj. Okay. Which will be equal to Rji. Okay. Now, if you look into the acceleration of the ITS body, okay. So, from here we can write the acceleration of the ITS body. So, RBI double dot, this can be written as RBRI minus RI double dot minus RB double dot. Now, we can check from the above equations that we have developed. This is Ri minus Rb. So, this we have written as Rbi. Okay. Now, we know that the barycenter of the system, this moves with a constant velocity, therefore, Rb double dot, the acceleration will be 0. Okay. Therefore, this gets reduced to Ri double dot. So, this has a very simple implication, and this says that thus equation 2, this is this we write as equation 6 and this is equation 7. Okay. Thus equation 7 has very simple implication that equation of motion does not change in different inertial reference frame. Okay. So, whatever the acceleration is in the x y z reference frame for the ITS particle, this is indicated by Ri double dot. So, the same acceleration it is noted, it is experienced in the barycentric reference frame, which is moving with a constant velocity. Thus, we can say that thus the equation of motion of the ITS particle is independent of any particular reference frame. This only depends on relative position vector RGI. Okay, so if we are considering the motion of the ITS particle, okay, so and there are n number of other particles present. So, it will just depend on the distance of the ITS particle from the JTS particle. Okay. And if we are considering, obviously last as we have considered for we have derived the formula that if we are considering about any particular mass. So, if we are considering the motion of a particle about any particular mass, then that mass constitutes the primary body and rest other they constitute as the perturbation body, or what we call the acceleration due to other particles, they act basically as a perturbation. So, that is the relative motion described here, but what we have just now looked into, this is the barycentric motion, means the point chosen, a reference frame chosen at the barycenter. So, this is an inertial reference frame, because it is a not accelerating, barycenter does not accelerate. So, it is a perfectly all right to choose the reference frame at the barycenter, and moreover the if the barycenter the reference frame fixed, it is not accelerating, and there moreover if we keep it parallel to the original reference frame. So, if and all the time means the original reference frame it is not rotating. So, the barycenter, the frame fixed at the barycenter, that is also not rotating, then it constitutes an inertial reference frame, and therefore, the motion of the ITS particle described in the original reference frame is as good as the motion in the barycentric reference frame. So, there is no difference, as we have concluded from this equation here, equation number 7. The generalized barycentric equation of motion can be written as RB L double dot. So, this is with respect to the barycenter, the motion of the LTS particle. In this case, we are taking this as the satellite. So, we can write this as RBS, this is the satellite, is equal to minus g times j is equal to 1 to n, j is not equal to L, and mj times RJL divided by RJL whole cube. Okay. So, this is the motion of the satellite, which we have indicated by L. L stands for satellite. Okay. So, this gives the motion of the satellite about the barycenter. So, now to solve the equation of motion, some approaches can be we can choose some of the approaches. So, we have suppose the first approach to solve the equation of motion, we have the following approach. So, we can opt for numerical solution, or we can do approximate analytical analysis. Why approximate? Because the exact solution anyway we cannot do. Okay. Therefore, if we can do certain approximation, so the it may be possible that we get certain kind of solution, and this gives a lot of insight into the motion of the system. Just like we have the earth and sun system, and or the earth moon system, and then we can have a satellite which is moving about the earth moon system. So, where earth is the primary body acting as the primary body. So, we can get a lot of insight into the motion of this satellite if we consider the approximate equation instead of just going through the numerical solution, because numerical solution it does not give us the generalized overview or generalized picture of the motion. So, whatever way we integrate, so it is a going to only describe how the particle trajectory is changing. Okay. So, the third one we can have exact analysis or exact treatment of the simplified problem. And fourth one, a study of general properties. Without solving the equation. Okay, so these are the four approaches we can choose. So, out of this we first do the fourth approach, we do the study of general properties of motion without solving the equations. Okay. And thereafter we will go into the exact analysis of the simplified problem. So, we will simplify the problem and then try to solve it. Okay. Study of study of general properties of motion. So, in studying these general properties of motion, as we have seen for the two body case, if we take the cross product, then we get the angular momentum term that was turned out to be a constant. If we take the dot product, then we got the result that total energy is constant. So, we apply the same approach for this system. So, the analysis it differs only in mathematical treatment, but the approach is the same, and we get also the same kind of result, and we will have little bit more insight into the problem for the three body or the multiple body problem. We will analyze it and see what really it reflects. Okay. So, going back into the our original equation, where we wrote the equation of motion as m I r I double dot for the ITS particle as g times m I times m j divided by r I j whole cube r I j. Okay. So, this is the equation of motion of the ITS particle due to the JTS particle, and we then sum over j is equal to 1 to n, where j is not equal to I. So, we are considering the motion of the ITS particle. This is r I, this is r j. Okay. So, the force on the ITS particle is directed along the r I j, therefore, here the minus sign is not appearing. Now, if we take summation of all the particles, so if we taking summation over all the particles, so I varying from 1 to n m I times r I double dot, this we can write as summation I is equal to 1 to n j not equal to I. So, this also we can write this term as f I j, that is force acting on the ITS particle, and then sum it up. Okay. J is equal to 1 to n and j not equal to I. So, we write this as equation number 8 and this is our equation number 9. Okay, so, this is nothing but I is equal to 1 to n and summation f I j, j is equal to 1 to n, j is not equal to I. So, if we look into the right hand side, and here we should give a vector notation to this, because this is a force which is a vector. So, here the property of this vector is f I j, this is nothing but equal to minus f j I. Okay. So, if we look into this summation, it is very easy to see that they will exist in pair. Okay. Suppose for the case where we have only two particles, so 1 and 2. So, here if we expand it, okay, here if we expand it, so we get f 1 2 and then we get minus f 2 1. So, these two terms will appear, and because both of them are equal in magnitude and opposite in sign. So, this indicates f I j plus f j I, this is equal to 0. So, right hand side this will be equal to 0. So, this simply implies that m I r I double dot summation I is equal to 1 to n, this will be equal to 0. Okay. So, this is our equation number 10. Okay. So, from here we can get to know that the we can reduce it to the equation for the center of the mass. Okay, and we will see that the center of mass of the system, it remains it moves with a constant velocity, that it does not accelerate. Okay. So, we continue in the next lecture. Thank you very much.